Good morning, it's Jeremy. It's Monday, December the 15th, an absolutely freezing day in Toronto. Today I'd like to talk about a very popular modulation scheme called QPSK, or quadrature phase shift keying, that's used in satellite communications, and a modification of that, the offset QPSK. So what I've done, I'm just looking at my blog post here. I've simulated the QPSK in Scicos. So here's a schematic to generate the QPSK. I'm using just simple parameters just to keep the computational math down. So I'm choosing a carrier frequency of 1 kilohertz, a data rate of 100 bits per second, and a symbol rate of 50 symbols per second. Each symbol is 2 bits. So basically what I'm doing is I'm generating random data here at 100 bits per second. I've got a demux which takes this 100 bits per second and splits it into 2 channels, one for the I channel at 50 symbols per second and one for the Q channel at 50 samples per second as well. So they're independent of each other. And basically what we have is complex modulation here. It's like e to the j omega ct, where we have cosine omega ct times the I data and sine omega ct times the Q data, and you add them together to give your QPSK waveform output. So here's, I'll look at the data. This is the data on the I channel, and this is the data on the Q channel. So the data can be plus or minus 1 on I and plus or minus 1 on Q. And you see when the data changes here on Q, you see a notch in the output sine wave carrier. So the first bits of data here, I would be 1, and down here would be minus 1. So 1 and minus 1 would give you this state down here. This is a constellation diagram. It gives you 4 possibilities for the output. Again, that's where the QPSK comes from, the Q. So 1 and 0 give you a plus 1, and 0 is a minus 1, or the state at 315 degrees. And the data can change from nearest neighbor to nearest neighbor, or across diagonally as well. So this is the XY scope here, showing you the generation of the constellation. We can look at the actual model here. I've got it open in Scicos. So what I'll do is I'll focus on the I pattern here. Sorry, not the I pattern, the constellation. I'll just simulate and run this. So there's the constellation. You can see how it's changing from nearest neighbor to nearest neighbor, and sometimes diagonally as well. All right, so let's go back to the blog post. So let's look now at, incidentally, this is the spectrum. The output spectrum, the main lobe is sine x over x, and it goes from minus 50 hertz to plus 50 hertz. So basically the bandwidth is actually 100 hertz, or equal to the bit rate here for QPSK. Now let's look at offset QPSK. It turns out when you're building a receiver, if the data changes on I and Q at the same time, let's say they both go positive, they both go negative, you get this diagonal 180 degree phase shift, and that can be a problem in receivers. So what they did is a modification to QPSK called offset QPSK. So it's exactly the same diagram as before, except you have a delay here, and you delay it by 1 bit. So if I look at the data, you can see here now that the Q data has been delayed 1 bit from the I data. And the reason for that is so you don't have this edge going up and this edge going up at the same time. So there's the output waveform as before. And here is here's the constellation, same constellation, but notice here now on the constellation XY graph from Scicos that you don't have any diagonal changes in state, or 180 degree changes in state. Again, you have the same output spectrum. Let's look at that model here. So I'm going to change my model here to the offset. So there's the offset. And again, we'll focus on the XY scope here to show the constellation. This is just the start here. So notice that you have the 4 corners, but you have no diagonal changes, or 180 degrees phase. So finally, where do we use this? Well, Here's an example from a previous video. I looked at the METEOR weather satellite, and the METEOR weather satellite M2-3 transmits data at 72 kilobits per second. And you can see that this spectrum here, the spectrum has the shape of OQPSK. This is a 100 kilohertz window here on the SDR sharp, and you can see that this fits in here. So the spectrum looks like it's around 72 kilohertz wide, plus or minus some filtering. Maybe it uses a raised cosine filtering, extending that a little bit, but you can see that that's basically what we've been looking at. And when you decode the METEOR signal in SatDump, this is what you get. You get the 4 points here in the constellation diagram. Historically, QPSK is quite interesting. Way back when I started my career in the 70s, Canada was converting its analog microwave to digital, and they started off with a very neat idea, and they put in a subcarrier above the analog baseband. They put in a 1.544 megabit or T1 signal using QPSK. It was called data above voice. This was a system that was pioneered by Dr. Camilo Fairhair. So QPSK has a long history. It's well understood, and it's a very robust modulation scheme.